Welcome to this module of computer aided power system analysis. So far till the last lecture we have discussed about the basic Gauss Seidel numerical method. In this lecture as well as in the next lecture we would be looking into the application of that basic Gauss Seidel numerical method for the solution of the power flow equations of any power system to compute the voltage magnitudes as well as the angles at all the other buses. So, to start with, we first recapitulate the basic Gauss Seidel numerical methods briefly, so that we can immediately connect those equations to the problem of solving the power flow equations at hand. So, we start. So, basic Gauss Seidel load flow, I mean it will be a very short introduction again, I mean it is just a kind of recapitulation. So, what we have, we had that our unknowns, there are n unknowns x2 to xn, these are unknowns. Then we have n equations, these are all non-linear equation, no particular form of these equations have been assumed. So, no particular form of these equations have been assumed. Now, we have seen that from these equations we would be explicitly representing x1 in terms of some other function g1 of all the variables x1, x2 to xn. Similarly, x2 would be g2, x1, x2 to xn dot 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 xn is equal to gn x1, x2 to xn. So, after that what we do, we take initial condition. So, the steps are take initial condition, so we take initial condition, then what we do, we update x1, x2 to xn, then what we do, we check for convergence, if yes then we stop, otherwise we go to if yes, if converged stop, else go to step 2. Of course, this is a very brief recollection of this basic procedure of the Gauss Seidel numerical method. So, we would now apply this in our problem. So, what we do, so now we consider an n bus system. So, we consider an n bus system, and to start with we assume that there is only one generator. Of course, we would be relaxing this, but we would, so there is only one generator and rest are load bus and rest are load buses. Of course, we would be relaxing all these assumptions in a little later stage, but just now we are making this assumption just to introduce the basic Gauss Seidel load flow method. So, now because we have got only one generator, so that generator is a slack bus. So, this generator is slack bus. So, V and theta are known. So, at this bus, as we have already collected, because this is a slack bus, voltage magnitude and its angle are known. In fact, angle of this particular bus is taken to be 0. And because these are all load buses, so all load buses all load buses P and Q are known. So, injected power at these load buses both real and reactive, they are all both known because these are load buses. Now, we have already seen in the earlier lectures that any n bus system, whether there is any mutual coupling between any two elements or not, any n bus system can be represented by its Y bus matrix. So, this Y bus matrix relations can be represented as I1, I2, In. So, this is Y11, Y12, Yn, Y21, Y22, Y2n dot Yn1 by N2 dot Yn, and here you have got V1, V2 to Vn, and these are all complex quantity, these are all complex quantity. As we already know that this vector I1, I2, In is nothing but the bus injection current vector. V1, V2, Vn is nothing but the bus voltage vector, and this matrix Y11, Y12, Yn, etc. This is nothing but the bus admittance matrix. We have already seen that how this bus admittance matrix is formed, and we have also looked at some of its properties. Now, from this, for any ith bus, we can write down that Yik Vk. So, we take the ith index not equal to I Yik Vk. So, what we did here, we have done a very simple thing, we have simply taken out the ith index here from here, and then we have simply put the other terms together. So, then therefore, we can write down that Yi Vi is equal to I minus k is equal to 1 to n not equal to I Yik Vk. So, then therefore, we can write down Vi is equal to 1 by Yii I minus k is equal to 1 to n, this is not equal to I Yik Vk. Now, we also know that at any bus Vi, that is the bus voltage, multiplied by the complex conjugate of the injection current, that is equal to Pi plus jQi, where Pi is the injected real power at bus I and Qi is the injected reactive power at bus I. So, then therefore, from here we can write down Ii star is equal to Pi plus jQi by Vi, or in other words Ii is equal to Pi minus jQi by Vi star. So, then therefore, we replace this in this equation. So, from here we can write down 1 by yii pi minus jqi by vi star minus k is equal to 1 to n not equal to I yik vk. So, then therefore, this is the equation for Vi. So, you can see that this equation of Vi is actually in the form of that Vi is equal to some function gi of the function v1, v2 up to vn. So, then therefore, we can write down that as if that Vi is some function of g1 of it should be gi v1 v2 to vn. So, it is exactly in the same form as we have considered in the case of basic Gauss Seidel numerical method. Now, here before we apply the basic Gauss Seidel numerical method, here we need to do something more. Now, here we have to see that when we are writing down the expression of Vi here at the right hand side for this summation, this Vi term does not exist. So, then therefore, we can simply write it down as yii pi minus jqi to Vi star minus. So, you would be simply breaking this into two parts. In the first part, we would be taking k is equal to 1 to I minus 1, then it is yik vk, and in the second part we would be taking k is equal to I plus 1 to n yik vk. What we have done here, because this term does not have the term Vi here. So, then we have simply taken the term from 1 to I minus 1 together and then the terms I plus 1 to n together. So, this is the final equation. So, we again write down this equation just to recollect, so that we have, finally we have Vi is equal to 1 by yii pi minus jqi by Vi star minus k is equal to 1 to I minus 1 yik vk minus k is equal to I plus 1 to n yik vk. Now, to illustrate this, let us take a very small example. Suppose n is equal to 6. So, let n is equal to say 6, and we are trying to write down, and bus 1 is the slack bus, and bus 2 to 5, 2, 3 to 6 are load buses. And we are trying to find out, we are trying to write down the expression of V4. So, in the original expression of V4, what we can write down is this is y44 P4 minus JQ4 V4 star, then minus y41 V1 minus y42 V2 minus y43 V3. This fourth term of V4 will not come here, then minus y45 V5 minus y46 V6, all are complex quantity. So, this equation we have written following this expression. Now, we take here, so it is y44 P4 minus JQ4 V4 star. Now, we take these three together. So, it is, we can write down that it is k is equal to 1 to 3 y 4 k v k, and then if we take these two together, we can write down k is equal to 5 to 6, this is y 4 k v k. So, all these are complex. Now, here we need to notice that, so here in this expression I is equal to 4. So, this is I. So, this is I is equal to 4. This 3 is actually is I minus 1. So, this is I minus 1. This 5 is actually I plus 1, and this 6 is equal to n. So, this is exactly this form what you have got. So, then therefore, we can write down this original equation in the more second form by this. So, we have simply decoupled the terms which is coming before the ith bus in the sequence, and we are taking together other terms which are coming after the ith bus. Now, as we have already said, when we are trying to solve any set of nonlinear simultaneous algebraic equations, we need to take an initial case. Now, here our unknowns are all voltages and essentially all voltage magnitudes and all voltage angles except the slack bus, because at slack bus everything is known. Now, what should be the initial guesses? So, that is very important. Now, fortunately in power system, what we wish to do is, power system we wish to maintain the voltage profile in this system at the nominal value, because if we can maintain the voltage profile of the system at the nominal value, that is the most optimum case, because if it is higher than the nominal value, so in that case there will be more stress, and again if this are lower than the nominal value, so then in that case there will be other problems such as under voltage problem, loss would be increased, etc. So, then we always wish to maintain the voltage profile of any system at the nominal level, and voltage magnitude, I should write here voltage magnitude at the nominal level. So, that means in per unit we wish to maintain it, we wish to maintain the voltage magnitudes at (1.0) per unit. So, then therefore, because we wish to maintain the voltages at 1.0 per unit, so it makes sense that we should take the voltage magnitude initial value as equal to 1.0 per unit for all the buses. But then the question comes, what should be the angle? Now, we know from our basic understanding of the power system operation, we know that if we have a line between any two bus let us say I and bus j, so then therefore, and if this bus has got angle theta I, we are not right now bothered about this voltage magnitude. So, if this angle is theta I and if this bus j has got an angle of theta j, and if the difference between theta I minus theta j difference is let us say more than 30 degree to 35 degree, so then usually we face the problem of the transient stability. Now, this we know from our basic understanding of the power system, and we can also infer this from the understanding of our equal area criteria. So, then therefore, essentially what we are trying to say is that if the angle difference between any two buses over a line is large, so then therefore, that particular line will be more prone to the problem of transient instability. So, then therefore, to make the system more stable, we would always like to maintain the angular difference between any two buses as small as possible. Now, in the case of slack bus, we have already assumed that our theta is equal to 0 degree. So, then therefore, by the same logic, because we want to maintain the stability of the system essentially, so then by the same logic, all the bus voltage other angles also should be as close to 0 degree. I mean, they can be little more positive, they can be little more negative, but then they should be all around 0 degree within a certain zone. So, then therefore, it basically makes a lot of sense if we take the initial value of all the bus voltage angles at as 0 degree. So, then therefore, by this logic, when we take the bus voltage magnitude initial value as 1.0 and the bus voltage angle initial value as 0 degree, this is called flat start. So, then what we are doing, we are taking, so we take initial guess as Vi 0 is equal to 1.0 angle 0 degree for all I is equal to 2, 3 to n. Please note that this 0 suffix or within the parenthesis denote that this is the initial voltage. Now, this case, when we are taking the bus voltage magnitude initial guess to be the same as well as the bus voltage angle initial guess to be the same for all the buses, we call it flat start. Flat start. Flat means the same. So, then therefore, we say that it is a flat start. That means that we are taking the bus voltage magnitude as well as the angle initial assumptions to be the same at all the buses, and this magnitude is 1.0 per unit for all the buses and this angle is 0 degree for all the buses. So, then therefore, with this, so now we can start writing our algorithm. So, then what do we want to do? So, the algorithm steps. So, then algorithm steps. So, the first algorithm step is assume flat start as the initial guess. Then we set iteration count say j is equal to 1. Then what we do? Then we update all bus voltages as Now you see, in this case we have assumed that the bus 1 is the slack bus, so then therefore the bus voltage magnitude and angle at this bus is known, so then therefore we do not have to solve for it, we have to only solve for the other buses. So then we will start our calculation from bus 2 and then bus 3 and then we will go up to bus n. So we start with bus 2, so then bus 2, the voltage at bus 2 updated value V2J. Now remember here when I am writing J, so this J stands for the iteration number J. Now please note that we have already set J is equal to 1 here, so then essentially it is actually V21. So it would be 1 by Y22 P2 minus JQ2. Now here I have to also put some V2 value. Now when I am trying to put some value of V2 at the right hand side, what value I know? I only know the initial guess, so that means that is 0. So then what I know is, so what I write is V2 J minus 1. Now because here J is equal to 1, so then therefore J minus 1 is equal to 0, so that means it is actually V2 0, right. So we should write that Vi is equal to 1.0 angle 0 for all I is equal to 2 to n, fine. Then minus, now because we are now talking about V2 and then we have got V2 and we do not have to solve for bus 1. So then therefore in this expression this term does not exist, because here in this case I is equal to 2, so then therefore it is k is equal to 1 2 1, but then I do not have to solve for 1 because bus 1 is already the slack bus. So then therefore I have to only take this part, so then it would go as k is equal to 3 to n V 2 sorry it would be y to k V k, it would be j minus 1, it would be j minus 1. J minus 1 means that here also we are simply taking the initial value, j minus 1 is equal to 0. So here also we are taking the initial value. Now after that when we are trying to solve for V3J, so V3J, now this is interesting, V3J it would be 1 by Y33 P3 minus JQ3. V3 we have not as yet solved, so V3 J minus 1. So V2 we have solved, so then what we will write is k is equal to 1 to 2 V3 k, so this is Y3k Vk j. Remember, for bus 1 it is already known and for bus 2 we have just now calculated. So we would be actually utilizing this bus voltage V2J. So we would be utilizing, so then from here when let us say k is equal to 1, it would be Y31 V1J, J is equal to 1, but then because this particular voltage of the slack bus is always held constant, so then therefore for bus 1 it is always the same, and then when k is equal to 2 then it would be actually V2J, and this V2J we have already calculated in the last step. So then therefore this is, and then from k is equal to 4 to n Y3k Vk j minus 1. But for bus 4 and onwards we have not as yet calculated. So then therefore for these buses we would be only utilizing the value of the voltage as we have assumed as the initial condition. Now here I guess one is missing, so in fact it also should be y2 to 1 V 1. So, then like this, if we go for V I at the jth, so I got Y I P I minus J Q I, V I you have not as yet solved, it should be all V I star J minus 1, here also it should be V 2 star, it should be here V 2 star. Then what we have? We have k is equal to 1 to I minus 1 Y I k. Now, for all the buses before I, that is up to I minus 1th buses, we have already solved for them at this present iteration. So, we will utilize this present iteration, and for the other buses k is equal to I plus 1 to n, we would be only utilizing the initial guesses. Dot 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 for V n j, it would be y n n p n minus j q n. V n we have not as yet solved for, so it would be j minus 1, still the previous one. And then what we will do is k is equal to 1 to n y because when I am solving for nth bus up to all the other buses n minus 1 we have already solved, only the, so only this part would be remaining. So, for up to all this bus we have already solved, and the for this nth bus it has already come into picture. So, these are the equations. So, after this what we will do? We go to the next step. So, in the next step what we do? Calculate error as E I at jth iteration as V I at the jth iteration minus V I into j minus 1th iteration, this mod for all I is equal to 2 to n. Then calculate maximum error as E max at the jth iteration as max of E 2 j, E 3 j dot 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 E n j, and then if E max is less than some epsilon, stop, else increment the iteration count and go to step 3. So, this is the basic equation, and this is the basic approach for solving the Gauss Seidel load flow with an single generator. So, in the next lecture we will be continuing this lecture and will show how this particular method can be used for solving a power system in which there are multiple generators. Thank you.